Again, one of the important thing of why where we're learning logic and propositions and quantifiers and all of that is because we really want to head to the point of what it means to have a proof of a statement and how do we write proofs. So now I will transition into that part and start talking about what is the notion of a proof and how we establish them in general. Okay, so proofs are all about valid arguments. Okay, so a valid argument is an argument that we make to establish the truth of a mathematical statement. So it's a mathematical statement is a proposition that's either true or false, and when someone claims that statement, we need to show that it is true. Okay, so there are two words there when we are talking about a proof. There is valid and there is argument. What is an argument? An argument in our sense here is a sequence of statements that end with a conclusion. So I'm trying to prove a point. That point has to be a sequence of statements. So there's the first statement, the second, the third, the fourth, the fifth, and the sixth, let's say, is the last statement. That last statement, the sixth one, need to be the conclusion that we were after. So if I want to prove that x is greater than 19, the last statement in that sequence should be x greater than 19. Okay, so it has to be a sequence and order on these kind of statements that takes me all the way from the assumptions that I'm making all the way to the conclusion I want to establish. What does it mean to be valid? Of course, we don't want to jump from one statement to another by magic or by invoking rules that nobody knows where they came from. What we mean by valid is that the conclusion has to follow from the truth of all the statements that preceded it. So when I write, actually, it's not just about the conclusion. When I write a proof or an argument that is a sequence of 6 statements, each one of these 6 statements the truth of it should depend on the truth of the preceding statements or axioms that we know about, or theorems that we have already established, and so on. Okay? Now, the argument in propositional logic is really just a sequence of propositions. Okay, so we have first proposition, second, third, fourth, and so on. All but the final proposition are called premises. The final one is the conclusion, because we are trying to make our way all the way to the conclusion. It is valid if the truth of all the premises implies the conclusion. Notice that there is a conjunction in this third bullet here. When I say the truth of the conclusion follows from the truth of all of its premises. So if the argument is 6 steps and the 6th is the conclusion and the first 5 are premises, then the first 5 are propositions. So we have the first one, the second, the third, fourth, and fifth. The conjunction of all these implies the conclusion. Okay? An argument in propositional logic is such a sequence of compound propositions, and it is valid no matter what particular propositions we take, then the conclusion has to be true. Okay? To establish proof and to establish such an argument and such a sequence of proposition, we need to go from one line to the next in our proof, or from one statement to the next, or from one proposition to the next. The way we do that in general is by using rules of inference. Of course, we have seen one other way to go from one proposition to the next, which is through equivalences, right? So if I have a proposition P and I know it is equivalent to Q, I can write on the second line or the next step in my argument Q, right? So I can go from P to Q, and the truth follows from the fact that P and Q are equivalent. Now, another way to do that is by rules of inference. Okay, so we infer the truth of a proposition from the truth of conjunction of other propositions. Okay, so here's one basic important rule of inference. It's called the simplification rule. What this rule says that if you, in your argument, you got to a point where you establish that P and Q is true, then I can infer from that P is true as well. Why is that true? Because if P and Q is true, remember that this compound proposition is true only in one case, when P and Q are both true. So if you tell me P and Q is true, I can conclude that P is true. In fact, I can conclude also that Q is true. But suppose I'm just going after P itself, I can conclude from P and Q that also P is true as well. Okay? In other words, this statement of P and Q implies P, that's a tautology. Okay, so if you try to build a truth table for this proposition, P and Q implies P, you will find that this evaluates to true no matter what P is, no matter what Q is. Okay, so in other words, that suppose I'm writing a proof, and the proof is really a sequence of these propositions. So I started with the first proposition, the second, and then the third. Suppose on the third, I established that P and Q is true. I can jump to the conclusion, whether it's in the fourth or whatever step. It doesn't have to be the fourth. Suppose it is in step 10. I can say that P is true. What is my claim? What's the rationale that P is true? I can say P is true because of simplification applied to step 3. So if I apply the simplification rule to step 3, I can establish the truth of P. Okay, this is what I mean by rule of inference, that if you got to a point that you establish P and Q is true, using the simplification rule, you have given me something for free, which is that P is true. Another very important rule of inference called modus ponens. Suppose you got to a point that you establish that P implies Q is true, and then later you establish that P is true. I can infer from this that Q is true. Why is this the case? Because remember that P implies Q. If P is true and Q is false, then P implies Q is false. Since P is true and P implies Q is true, Q has to be true. Okay? So again, how do I use modus ponens? Suppose I'm establishing a proof and I started with step 1, and then I get to 3 and I show that P is true. Then I get to line 5 and I show that P implies Q. From these 2, 3, and 5, I can actually write that Q is, suppose again on line 10, I can write that Q is true. What's the rationale or justification for that? I can write that it is because of the modus ponens rule applied to 3 and 5. Okay? So if in my proof I got to a proposition that P is true, to the step that P is true, and I reached later that step that P implies Q is true, I can immediately infer that Q is true using modus ponens rule. Okay. Another rule that makes sense and it's very important, this is what sometimes we relate to or call the notion of transitivity. If P implies Q and Q implies R, then I can infer that P implies R as well. Okay? So again, if I, in my proof, on one line I established P implies Q, on another line I established Q implies R, then I can immediately conclude using hypothetical syllogism applied to these two lines that P implies R as well. And these are just examples, just 3 examples of rules of inference, because there are so many other powerful rules. Some of them have names, some of them don't have specific name. Memorizing the names is not an important thing here. What's important is to remember that these are rules that are correct, that they are valid, that you can use in proofs. Modus tollens is similar to modus ponens here, but suppose I say I prove that P implies Q, but I establish that Q is false, P must be false as well. Disjunctive syllogism, if I establish that P or Q is true, but P is false, well, if P is false, for P or Q to be true, Q has to be true. Okay, this is disjunctive syllogism. And conjunction is simple. If you establish 2 propositions to be true, P and Q, then their conjunction is true. Resolution is powerful. Look at it here. We are saying P or Q is true. We are saying not P or R is true. Well, think about P. If P is true, then P or Q is true. But if P is true, not P is false, R has to be true. If P is false, then for the first one to be true, Q has to be true. This is why if you prove that P or Q is true, and you prove that not P or R is true, you can conclude from this that Q or R must be true. This is the resolution rule. The last one is that the addition. If you prove that P is true, P or anything would be true as well. Okay? And now we can use these rules of inference to prove other results. So for example, suppose someone say, can you prove to me that if P and Q or R is true, and R implies S is true, then P or S is true. And one way to do this proof, again, is by using rules of inference. And the way we would do the proof is as follows. We make use of assumptions. What are the assumptions that are given in this exercise here? This is one assumption, assumption 1. And this is assumption 2 here. Okay, these are the two assumptions we are given. This is the conclusion we want to prove. Okay, so to establish the proof, for example, I can do it step by step. So the first step here is I can say, I know that P and Q or R is true. Why do I know that? Because it's an assumption. Someone told me to assume that this is true, assumption 1. The second step here is that I know that R implies S. This is assumption 2. So I know this is true. Someone told me to assume it is true. So now I can start using equivalences and rules of inference, and remember that my goal is to reach that conclusion P or S. Okay? So if I look at R implies S, I know that this is equivalent to not R or S. This is equivalent to 2. Right? So this is not the assumption 2, but to R implies S, that what's written on line 2. The other thing is that I know that we have P and Q or R. I can up the first one, assumption 1. I can actually say that this is also R or P and Q. So what did I do here? I just applied the commutativity to line 1. Okay, so this is equivalent to line 1. Okay, so now look what you see, something that should jump at us immediately, and from one of the rules of inference. Look at the third line. It tells me not R or S. The fourth line, R or something else. One of the rules of inference tells me that if I have these two propositions, one involving not R or something, the other one R or something, I can actually conclude from this that I have S or P and Q. So here I applied the resolution rule. Resolution applied to 3 and 4. To 3 and 4. I get to S or P and Q. Okay. Now, I can now say that I can use the distributive law, which is for equivalence, and I can say that this is S or P and S or Q. So this is equivalent to 5, right, by the distributive law. Now, if you look at this, that I established S and or P and S or Q, the simplification rules tells me that if I establish the conjunction of the two propositions, and either of them is true, right? So S or P is true. This is by the simplification, applying the simplification rule of inference on line 6. The last thing is, notice that I'm trying just to be too formal here. The conclusion is not S or P, it is P or S. But we know that S or P and P or S are the same because of the commutativity of disjunction. So this is equivalent to 7. And now we are done, right? Because this is the conclusion we wanted to establish. So look at this. This is a formal proof in which on every line, if you look at it, I either used an assumption, someone told me to assume these are true, or I stated something that is equivalent using equivalence or rules of inference based on the lines before it. Okay? And the very last one was the conclusion. So this is a valid argument that took me all the way from the two assumptions, 1 and 2, to the conclusion. Okay. Now, these are what we have talked about for rules of for statements that don't involve quantifiers. What if I want to prove some statements that have quantifiers? So to prove something that has quantifiers, the first thing we want to usually do is get rid of the quantifiers, right? So we want to get rid of these symbols. So what does it mean to get rid of the quantifier for all x when we're talking about P of x? Basically, when someone says for all x, P of x is true, then they say if you take an arbitrary a, P of a is true. any arbitrary a, right? So instead of keep working with for all x p of x, I can now just replace that by p of a. This is known as universal instantiation. But notice that the a here is an arbitrary a, not a specific one. If I'm talking about existential quantifier for all x p of x, the rule of inference is to say p of a is true for a specific a, for some a, right? And towards the end, if I'm trying to establish a result that has quantifiers on it, I now can start going back from statements that don't have quantifiers to statements that have quantifiers. So for example, if I showed that p of a is true for an arbitrary a, I can turn that into for all x p of x. And this is what we call universal generalization. If I establish that p of a is true for a specific a, then I can turn that into their existent x such that p of x. This is called existential generalization. Okay. So suppose I want to use the rules of inference to establish this. So here we have, again, let's label them here. So we have this assumption 1, we have the assumption 2 here, and we have this assumption 3 and assumption 4, and we want to reach this conclusion. Okay, so there are lots of assumptions and one conclusion here. Assume 1, 2, 3, and 4, establish the last one. Okay, so to establish this, again, we can start, usually we would start from assumptions. We start massaging them through rules of inference, through equivalences, and so on to get to the conclusion that we want. So I can start with line 1, and I can say the first assumption tells me that for all x, p of x or q of x. So again, this is assumption 1, okay? Line 2, I can now use universal instantiation, and I say this is the same as, or from this I can conclude p of a or q of a for an arbitrary a, right? This is universal instantiation. In the third line, I can now go to one other assumption. Okay, I cannot do much more with this. It's p of a or q of a. Let me go now to a second assumption here. For all x, not q of x or s of x. This is assumption 2. And again here, since it's universally quantified, I can now also say that this is not q of a or s of a for an arbitrary a as well. This is again universal instantiation. Okay, so now look at lines 2 and 4. I'm not going to use commutativity here. I'm going to actually take a shortcut. Line 2 says q of a or p of a. Line 4 says not q of a or s of a. Using the resolution rule, I can conclude from this that I have p of a or s of a for an arbitrary a. And this is resolution on on lines 2 and lines 4, okay? By resolution. 6, let me now, again, I got to p of a or s of a. I cannot do much more with that. Let me look at another assumption here. For all x, r of x implies not s of x. This is assumption 3 here, okay? Now, again, I can use universal instantiation, and I can say what this is saying is that it is r of a implies not s of a for an arbitrary a as well. So this is universal instantiation on line 6, right? And now I can look at this and I can write something. Again, usually the implication, remember there's an important equivalence for implication. P implies Q is the same as not P or Q. Okay, so I can now say that this is not RA or not SA. This is equivalent to line 7. Not R of A, not S of A. This is equivalent. Okay. And now for line 9 here, I can say that we have not R of A or P of A. Okay, where did I get this from? So if you look at line 8 and line 5, okay, again line 8 and line 5. Line 8 has not S of A, line 5 has S of A. Both of them have disjunction. I can use the resolution on this. So not S of A or not R of A. One of them says S of A or P of A. Therefore, P of A or not R of A has to be true. So this is resolution on lines, what did we say, 5 and 8. Okay? And again, we are still with an arbitrary A here. Now, we go to the last assumption here that says there exists an X, not P of X. This is assumption 4. I can immediately use existential instantiation on this. And I can say this is not P of, let's say, B for specific, for some B. This is no longer arbitrary, okay? So this is not P of B for some B. But look now at lines 9 and 11, okay? So line 11 says not P of B, okay? So for that specific B, P of B is false. If look at line 9, we are talking about every possible A, including when A is B really there. So when A is B, for that specific value is B, then the right-hand side in not R of A and or P of A is going to be false, right? So when not P of B is true, it means P of B is false. From lines 9 and 11, using the resolution, we can include that it is not R of B for some B. So this is resolution on lines 9 and 11, okay? Now what did we get to? Line 12 is that not R of B for some B. So there is some B such that R of B is false. I can use now existential generalization, and I can say this is exactly as saying there exists an X such that not R of X. This is again existential generalization on 12. Okay, and this is the conclusion that we were going after. Okay. So if you look at this again, I used just the assumptions, I used equivalences, I used rules of inference all the way to get to the conclusion. Now, one important point again to raise here and to emphasize once more is that one could ask, why did we choose these steps in this specific order? And how do we know, for example, that on line let's say 5, that we should have used the resolution rule? Well, again, this is why establishing proofs is not a trivial task. And this is why exercising more and more with this kind of tasks is what helps one build more experience with establishing proofs. Once again, there is no procedure that we can teach and you follow this procedure and you prove whatever you want. Proofs, again, as you look at this, proofs as an art. I mean, one could have actually established this proof, but maybe have taken so many more steps or even fewer steps to establish that proof. To get to establish these proofs, remember that you always make use of the assumptions, and you assume they are true because they are given to you. You use logical equivalences, you use rules of inference as well, and you make sure that you write your proof as a sequence of these propositions. Then you have a proof. Okay, so a proof, again, a proof is such a valid argument which is a sequence of propositions that use equivalences and rules of inference. And when we prove something, when we prove a result like on the previous slide, now we have a theorem. That theorem is there, you can make use of it. And the theorem is proved using the proof technique. And not only do we use the assumptions, not only do we use rules of inference and equivalence, but you could use axioms as well. These are results that don't require proof. So here are some examples of axioms on real numbers, right? So you can make use of the fact that if x is a real number, x plus 0 and 0 plus x are the same and both of them equal x. This does not require proof, it doesn't have proof. This is just an axiom of the real numbers. You can make use of the fact that if x and y are two real numbers, their sum is also a real number. You can make use of these in a proof. So you can use the assumptions, you can use axioms, you can use rules of inference, you can use logical equivalences as well. Okay? And again, we usually try to prove theorems, but sometimes also there are Just like when we write a program, a computer program, we don't write a program that consists of just one function consists of 1,000 lines of code. We break it into smaller functions and we start calling them. This is the whole notion of having libraries in programming languages so that you can invoke functions without having to rewrite everything from scratch. The same thing with proving a theorem. Sometimes if the proof of a theorem spans 1,500 pages, we don't want to write the proof like that. We break it down into smaller results, establish them, and then we make use of all these results to prove the theorem. These smaller results are lemmas or corollaries and so on. Now, we have lots of claims in mathematics. Usually they are made by experts in the field. These claims sound to be true. They seem to be true. Nobody has been able to show that they are false. But in that case, we call them conjecture. We don't call something a theorem until we have a proof for it, right? So there are conjectures. There are famous conjectures in mathematics and in computer science. They are conjectures so long there is no proof for them. Once a proof is established, and the proof is correct, of course, then that conjecture becomes a theorem.